Welcome back to the deep dive. Today, we are moving past the theoretical speed of light and focusing on the meticulous engineering required to make sure data actually gets where it's going.
Right.
The sheer performance of modern high-speed networks, fiber optics moving petabytes of information, it all rests on one single, precise calculation.
And that calculation is, well, it's the single most essential design challenge for any modern network engineer, the fiber optic link budget.
Exactly.
You sent us sources that dive really deep into the math behind reliable data transmission, which is, at its core, fundamentally about defining the limits of light.
And our mission for this deep dive is to extract that blueprint for success. We need to analyze this link budget so we can guarantee two things. First, that the light signal is strong enough to be detected at the other end.
So avoiding too little power.
Right. But at the same time, that it's not so strong that the receiver is overloaded, or, as the sources charmingly put it, blinded.
It is a very, very fine line. And to navigate it, we have to operate in the world of decibels. So before we get into the budgets, maybe we should quickly clarify the two essential measurements.
Good, yeah.
We use dB to measure relative change, so how much power was lost between point A and point B, kind of like a percentage. And we use dBm to measure absolute power, the actual amount of light being transmitted or received.
Like the absolute fuel left in the tank.
Exactly. That's a perfect analogy.
So we're looking for that sweet spot. And to find it, we have to unpack three key concepts. The overall link budget, the calculated link loss budget, and the non-negotiable safety margin that really holds the entire system together. Okay, let's unpack these foundational concepts for you. Imagine you're building a bridge. The total load the bridge can safely handle before, it collapses. That's the link budget. Sometimes it's called the power budget.
Right, and it represents the maximum amount of signal degradation or loss that your network link can tolerate and still function perfectly.
So that budget defines the operating range.
It does. At the bottom end of that range, you have the receiver sensitivity. That's the absolute minimum amount of light you need to successfully decode the data.
And at the top?
At the top end, you have receiver saturation, the point where too much light just overwhelms the sensor and starts generating errors. The link budget is the total power difference between those two limits.
Okay, so then you have the link loss budget. If the link budget is the bridge's maximum load, the loss budget is, what, the estimated total weight of all the construction materials?
That's a great way to put it. The fiber, the splices, the connectors, everything you plan to install, it's the calculated theoretical loss based on component specs before the installation even begins.
And this is where we find the most critical concept for system stability, the link loss buffer.
Or safety margin.
The safety margin.
Yes. This is the difference between the maximum load, the budget, and your calculated estimated weight, the loss budget. Designers really stress this. You must build in a margin.
Typically between, 3 and 10 dB?
Exactly, and that seems like a huge range.
It is a huge range. What exactly is that margin covering?
Well, it's covering everything you can't predict in your spreadsheet. Fiber aging over 10 years, temperature changes, incidental bending that might happen during installation, and this is the big one, the inevitable repair splices that happen if a cable gets accidentally severed.
Right, the backhoe problem.
Your backhoe problem. You can't design a system based on just barely reaching the receiver with the minimum required light. That margin is the difference between a network working reliably and one that fails intermittently on a hot Tuesday afternoon.
Now here's the counterintuitive problem that requires a totally different approach.
Yeah.
Having too much power. Overloading. The irony is, if I spend all this money on the most powerful laser transmitter possible, I might be, signing my own death warrant.
You absolutely could be. What's fascinating here is that while we spend most of our time worrying about loss, the signal getting too weak, installing a more powerful transmitter is not automatically better.
So more power, more problems.
Sometimes. If the signal strength exceeds the receiver's specified maximum dynamic range, you don't just get a few errors, you can get complete signal failure.
And the sources point out this is far more common in single-mode fiber systems, right?
Yes, exactly. Because single-mode systems typically use these really powerful laser sources to achieve long distances. They're just pushing out a lot of light.
Yeah, and multi-mode.
Multi-mode systems, on the other hand, generally use cheaper, less powerful LED sources. So they rarely generate enough power to cause saturation, except maybe over extremely short patch cable runs.
So if you have a powerful single-mode transmitter paired with a sensitive receiver right next to it, and the link budget calculation shows you're going to saturate it, the answer isn't to buy new equipment.
Right? That's where fiber attenuators come in.
Sunglasses for your fiber.
Think of them as sunglasses for your fiber link.
Exactly. They're mechanical devices designed to just reduce signal strength. They work by absorbing, scattering, or diverging the light until the power falls safely within the receiver's acceptable range. Prevent saturation, but you still have a good signal-to-noise ratio.
You got it.
And we should always put the sunglasses on the receiver, not the transmitter.
Precisely. Attenuators are best installed at the receiver end. That ensures any minor reflection or backscatter caused by the attenuator itself doesn't travel all the way back up the line and affect the high-powered transmitter.
Which could cause instability.
Right. You can choose a fixed reduction attenuator or, for more control, a variable one that lets technicians fine-tune the signal power until it hits that sweet spot defined by the budget.
Okay, that was a complex set of definitions. To make this really actionable, we need to look at the physical realities. The link loss budget is calculated by identifying every single component that tries to steal that light signal.
And if we look at the formula for the link loss, it basically sums up 4 major components.
So what are they?
You've got your fiber attenuation, your splice loss, your connector loss, and of course your safety margin.
Okay, let's start with the biggest thief, fiber attenuation. This is the unavoidable loss inherent in the glass itself, usually provided by the manufacturer in dB per kilometer.
This variable generally has the single greatest impact on overall system performance. I mean, the choice of fiber and wavelength is everything.
So give us an example of the difference.
Look at this. If you're using standard multimode fiber at 850 nanometers, the loss can be as high as 3.5 dBs per kilometer.
3.5, that's a lot.
It is. And that high loss factor is why multimode fiber is pretty much restricted to short distances, usually less than a kilometer.
Contrast that with single-mode fiber, which uses lower loss wavelengths like 1310 or 1550 nanometers.
Exactly. The attenuation coefficient just drops to a fraction of that, typically 0.4 dBs per kilometer for long-haul routes. And that tiny difference in loss is what enables links up to 70 kilometers, supporting standards like 1000 base LH.
Okay, so now let's talk about connections. The TIA 568 standard sets a maximum loss allowance of 0.75 dBs per mated connector pair for certification.
It does.
Wait, hang on. That number seems really high.
It can be.
I mean, if we know that in these high-speed data centers, they need the total loss to be less than, what, 2.0 dB for the whole channel?
Yeah.
Isn't 0.75 dBb per connector pair actually encouraging mediocre performance?
That's a fantastic question, and it hits on a key insight from the sources. That high TIA limit of 0.75 dB is necessary because the standard has to cover really complex field-terminated components.
Like what?
Things like MPO assemblies or those pre-polished splice connectors, which just inherently introduce more loss. However, for high-quality, factory-made patch cords, the connection loss is expected to be significantly lower.
So less than 0.3 dBA ideally.
Ideally, yes.
Yeah.
Good designers will calculate their budget using that better, lower number, not the TIA maximum.
Smart. Okay, next up we have splice loss. What's the difference in light theft between the two main types?
You have mechanical splices, which align the fiber ends with a physical jig and some gel. This can cost you between 0.7 to 1.5 dB.
Not great.
Not great. Then you have the preferred method for performance, fusion splicing. This method physically melts and fuses the two fiber ends together with an electrical arc.
So it's a permanent, near-seamless connection.
Exactly. Fusion sounds better because it is better. Fusion splices introduce much less loss, typically calculated between 0.1 and 0.5 dBAB per splice.
So if you're aiming for high performance, you calculate with that lower number.
You do, though the TIA 568 standard allows a maximum of 0.3 dB for fusion splices for certification.
We've covered all the planned losses, but I think the single biggest reason a fiber link fails is often something completely unforeseen and physical. That's why we need that margin, right?
Absolutely. The margin is there to cover common culprits like macro bending exceeding the cable's minimum bend radius, which causes light to literally leak out of the core, and incredibly commonly, end-face contamination.
End-face contamination. It always sounds like such a small detail, but it's a huge problem.
It is the curse of the dirty finger. The core of a single-mode fiber is tiny, maybe 9 microns. A single particle of dust or oil residue from your finger is exponentially larger than that core.
And it can just block the signal.
It can block or scatter the signal, immediately increasing your loss by 5 dBs or more. Technicians spend hours troubleshooting a failed link only to find a microscopic fingerprint on the connector end. That's the real-world factor that eats up your precious safety margin instantly.
Okay, let's stop talking about theoretical loss and actually use these numbers. We'll look at two concrete examples to show you how engineers balance the ledger and make design decisions.
Sounds good. Our first scenario is about estimating total link loss. We need to determine the required transmitter power for a long run. So we'll use a robust long-haul example, a 40-kilometer single-mode link at 1,310 nanometers.
And this link has 2 connector pairs and 5 fusion splices. And since we're responsible engineers, we're adding a 3.0 dB safety margin. We'll use the TIA max assumptions for the components, so 0.4 dB per kilometer for the fiber, 0.1 dB per splice, and that 0.75 dB per connector pair.
Perfect. So we are calculating the estimated total attenuation we have to overcome.
Okay, let's break it down.
First, the fiber loss dominates. 40 kilometers times 0.4 dB KRMA gives us 16.0 dB. That's the bulk of the power consumed right there.
16 dB. Got it.
Then we have the components. Splice loss is 5 splices times 0.1 dB, so that gives us 0.5 dB.
Easy enough.
Connector loss is 2 pairs times 0.75 dB, giving us 1.5 dB. And finally, we add that crucial 3.0 dB safety margin.
So adding those up 16.0 plus 0.5 plus 1.5 plus 3.0.
The estimated required power for this link is a total of 21.0 dB.
And that 21.0 ED tells the engineer, your system must provide at least 21 dB of optical power difference between the transmitter and the receiver's sensitivity to survive this distance and have a reliable safety buffer.
Exactly. Now let's flip the problem for scenario number 2. Estimating maximum distance given a fixed amount of available optical power.
Let's say we're working with an older fast Ethernet single-mode link, again with 2 connector pairs and 5 splices. But this time, we know the available optical budget. The max power we can afford to lose is 26.0 dB.
Right.
How far can we push that light?
Okay, so we have 26.0 dB of total power to play with. First, we have to subtract all the power we know we're going to lose to components and safety. So the splices, that's the 0.5 dB, the connectors, 1.5 dB, and the non-negotiable safety margin, 3.0 dB.
So that totals 5.0 dB of loss we have to account for right off the bat.
Exactly. So we subtract that 5.0 dB from the 26.0 dB available budget.
Which leaves us with 21.0 dB.
And that 21.0 dB of power can be allocated solely to overcoming the fiber's attenuation over distance. Since we are using that same 0.4 dB KROM loss factor, we just divide the remaining power, 21.0 dB, by the fire loss factor.
And the result is an estimated maximum distance of 52.5 kilometers. That calculation determines the absolute physical limit for that specific electronic standard, using that quality of components.
Sure.
So you do all this meticulous math, you install the fiber, and now you have to certify it. This is where it gets critical for anyone in the field.
Mm-hmm.
Why are there 2 separate sets of standards that seem to contradict each other?
This is a point of frequent confusion, and it really highlights the difference between meeting, say, a construction code and meeting a performance requirement.
Okay.
First, you have the generic installation standards, like TIA 568. When a technician performs Tier 1 certification, what they're doing is guaranteeing the workmanship.
The quality of the install.
The quality of the install. They're confirming that the measured loss is less than the calculated loss allowance based on the physical components, and the TIA is pretty generous component loss maximums. It basically says, this cabling was installed correctly according to industry building guidelines.
But, and this is a big but, just because the cabling passed the installation test, that doesn't mean it can handle today's network traffic.
Exactly. That's where the network application standards come in, like IE 802.3 for Ethernet. These standards are much, much stricter. They set hard limits on channel loss and, crucially, on channel length specific to the data rate.
For something like 100 GB SR4.
For something just like that.
Why does the distance matter so much if the power is still strong enough to get there?
Because it's not just about the signal strength anymore, it's the speed of the data. At extremely high data rates, 100G and beyond, the light pulses start spreading out over distance. It's a phenomenon called dispersion.
So the signal gets smeared.
Think of it like a line of soldiers marching too far and losing formation. The receiver can no longer distinguish the individual pulses, so the application standard uses a maximum length limit as a proxy to prevent that dispersion, which is why TIA 568 testing does not guarantee your high-speed application will work if it exceeds the IE length or loss limits.
So here's the key insight. Higher speeds require exponentially smaller loss budgets and shorter supportable distances. You can't just rely on yesterday's infrastructure.
The requirements are brutal. 100G Ethernet links on multimode fiber often require total channel attenuation of less than 2.0 dB.
And the distance.
You're limited to 100 to 150 meters, depending on the fiber type. That's it.
That brings us to the ultimate challenge. Future-proofing a data center designed to last 10 or 15 years. How can engineers guarantee support for 200G or 400G applications that barely exist today?
The sources suggest that a conservative approach is absolutely essential. First, when designing, it is best practice to design the link out to only 70% of the maximum standard link loss budget.
70%.
Yeah, you're buying yourself crucial headroom for future unknown applications.
So the real insight here isn't just the math. It's realizing that high-speed applications like 400G are using the infrastructure itself as a kind of filter.
Yeah.
We are future-proofing our business by designing for performance we don't even need today.
Precisely. And that means component selection is paramount. If TIA allows 0.75 dB for a connector pair, you should be seeking out products that consistently perform at 0.15 to 0.25 dB loss per mated pair. That extra initial investment in high-quality, low-loss components is the only way to guarantee your infrastructure can support the speeds of tomorrow without having to rip everything out.
That was a tremendous deep dive. We've mapped the link budget, we've identified every single attenuation factor from fiber quality to the accidental dirty end face, and established the crucial need to design not just for installation compliance, but for application performance.
And I want to leave you with one final thought, revolving around the inherent imprecision in a field that requires such high precision. Remember, the loss budget calculation is an estimate. It's based on estimated component losses.
Right.
And the insertion loss testing, that relies on complex instruments that have their own inherent measurement errors. This means no number is absolute.
So the link budget is an estimate, and the measurement is an approximation. That's a powerful idea.
Right. So if your meticulously calculated loss budget is 8.0 dB, but your technician measures the installed link at 8.2 dB, immediate rejection might be a mistake.
Why is that?
Because the uncertainty in your calculated budget and the uncertainty in the measurement, they overlap. So a technician often has to exercise professional judgment to avoid failing a good fiber that might only be slightly outside the estimated boundary, or worse, passing a bad one.
So it's a field where math is the guide, but the application really relies on experience in knowing where to apply your safety margin. Thank you for diving into the critical world of the fiber optic link budget.
My pleasure.
We encourage you to apply this newfound knowledge next time you analyze your network infrastructure specifications.